So we're going to start talking about the more complex and more versatile inferential statistics, and we're going to start talking about how they are actually used, again, their assumptions, and a little bit of their history of where they've actually come from. But before we move on, I just want to briefly remind everyone that human behavior is very complex. If we're actually looking at behavior, at a minimum, we're looking at predictors of behavior, including your fixed traits, your personality, i.e., someone that's highly extroverted is more likely to do extroverted behavior. Someone that's highly introverted is more likely to do introverted behaviors. However, that's not the only predictor. It also manages about the social situation the person is in. So again, you put someone that's very extroverted in a situation that demands that they stay quiet and pay attention, they're more likely to do that. And likewise, you take someone that's highly introverted and put them in a situation that requires some form of interaction or social behavior, they're more likely to be more introverted. So again, we have that interaction. And on top of that, we have states and frames or the cognitive component. So again, we can have someone that's highly extroverted in a situation that would encourage extroverted, but they're in a very different frame of mind due to an event. They may be very sad because something just recently happened, which means again that their behavior would not be what we expected. So when we're actually studying human behavior, most studies are typically only looking at one component. What is the differences we find in personality and behavior? What is the differences in situations where we find behavior? What is the differences in states and frame of minds when we find behavior? And indeed, these are entire fields of psychology. There is the field of personality psychology, the field of social psychology, and the field of cognitive psychology. But if we're really wanting to get at behavior, we're probably needing to do an interactive model looking at all of those. So this doesn't have as much to do with inferential statistics. This is more of just a quick aside on methodology to discuss and to remind ourselves that though we often are looking at very specific studies that have found meaningful results of personality, meaningful results of the social situation, and meaningful results of states and frame of mind, cognitive. But if we're really wanting to try to get at better prediction of what someone is going to do in the future, we pretty much need to know all of these things. What's their personality? What's the situation they're in? And what is their current state or frame of reference cognitively? And that's going to give us a lot better of a predictive model. And usually that also involves incorporating multiple studies from multiple fields to really get at a good predictor of behavior. So having said that, let's start talking about inferential statistics, specifically the t-test. So in the next set of lectures, we're going to be discussing the t-test for between subjects and the t-test for within subjects. Hopefully you've already gone through the lecture on the differences between subjects and within subjects. So basically between subjects is referring to where we have different subjects in our comparison groups. And within subjects refers to repeated measures. In other words, we have the same subjects in our comparison groups. And there's different statistical expectations on requirements, and there's also different bars, if you will, for if we find significant differences when we're looking at this. So when we look at a t-test is simply comparing two groups. If we're comparing two groups that are completely different, we have to have different adjustments based on our prediction of how likely that difference would occur naturally if we found two different groups of people that we were going to study. Likewise, if we're looking at a t-test, the difference between two groups of people on a particular outcome, but it's the same people in both groups, we actually have a lower bar because we can make a better prediction at that point. So one is more powerful, but also comes with it some advantages and disadvantages. So unlike the previous lecture where we were talking about this theoretically, now we're really looking at the actual statistical tests and what we have to do to examine them. This set of lectures will be looking at the between subjects t-test. So we're going to be taking the t-test between subjects. Basically, again, one of our first assumptions is that there are two variables and that the measurement of the two groups is independent of each other. In other words, people from group one did not impact the behaviors of group two. So we have an independent variable that's categorical with two levels and a DV, an outcome that is continuous. Two variables, one IV, one DV, and in this case, that's our t-test. And that's what we're going to put in our toolbox as far as our ability to actually calculate this test. So the t-test is often referred to as the student's t-test, so that is progressive. And you'll notice we've already talked about the correlation, which was Pearson's correlation coefficient. So it was named after the person that actually invented it. In the case of students t-test, it actually isn't named after the person who developed it because he was under contract to the Guinness Beer Company at the time and couldn't put his name on this particular statistical technique he came up with. Therefore, it's commonly referred to as the students t-test because students used it initially. But the person that actually developed it was W.S. Gossett. So W.S. Gossett was working for the Guinness Beer Company, and he actually was creating a statistical mathematical way to compare different bouts or basically tests of beer. So you'd have a bunch of experts rating the quality of a beer from one batch, and they wanted to statistically compare it to the quality of beer of another. In other words, they were actually looking for non-significance. In other words, there's not really a difference from batch one to batch two. So he worked in the Ireland in the Guinness Brewery. It was mainly he was focused on comparing quality of beers. He was one of the key factors or key people in the development of Biometrica, which is pretty much still to this day one of the premier journals when we look at statistical techniques. He was also good friends with both Pearson, the developer of the correlation, and Fisher, who we'll be learning about soon, the developer of the ANOVA. And this is actually fairly significant because Pearson and Fisher did not like each other. Also, unlike most of the statisticians who developed these tests that we use that were British and were actually developing them initially to look for individual differences, and honestly were using them to determine that quote unquote British white males were superior to anyone else. Gossett really wasn't doing that. He actually just came up with a statistic to look at beer and actually did not hold any of these opinions, and he was Irish. So he was not a eugenist. He did not believe that there was a major difference per se, or at least he never published beliefs in this, that there was major differences between various types of people in the world. He was just interested in measuring the quality of beer, and that's where the t-test or student's t-test comes from. So let's talk quickly about the between subjects t-test assumptions, and these assumptions will be different than the within subjects t-test, which we'll be discussing later. So the first one, and it's a big one for the between subjects test, is independence of observation. Not only are there different people in each group or level of your IV, so if you have an independent variable at two levels, it's different people in each level of the test. They also are independent of each other. In other words, if you had a group of people that took your test and then immediately got to interact with your next group to tell them about the test or their responses, you've lost independence of observation. So it needs to be two different groups, and those groups need to be methodologically set up in such a way that they don't influence each other's scores. Our next assumption is the same across t-tests, whether it's a between subject or within subject, and that is that the DV must be normally distributed. There must be normality. So again, when we're looking at that outcome, it needs to be a continuous variable, and it needs to be roughly a normal distribution. There is also a requirement that the groups must have equal variance. This is called homogeneity of variance in the dependent variable or outcome scores. And this can be tested for you with the Levene's test. Now, this is important for you to set in your mind. The Levene's test is only asking, is there a significant difference in the type of variance between two groups? It is not looking for statistical significance. It is not comparing the two groups. It is simply asking, have you met the assumption of equal variances? And in this case, when you see the Levene's test of equality of variance, it'll appear in SPSS as an F statistic and a significance value. You're not going to report the F, you're not going to report the significance, but you will report whether or not it was significant. And you are wanting it to not be significant. You want the significance to be above 0.05, non-significance. Because what this is doing is it's not looking for a difference between the means. It's asking, was one group platykurtic, so a very flat distribution, and was the other group leptokurtic? Was one group normally distributed and one group not normally distributed? What it's looking for when it's significant is that there is a meaningful difference in the distributions, which means this violation of homogeneity, sameness of variance across your two groups has been violated. And it is no longer appropriate to look at whether or not there is a significant difference between the means of the groups. As long as this is insignificant, again, a t-test of above 0.05, it basically is just a green flag to continue with your analysis. So let's just talk about it theoretically, not mathematically. The between participant design, we have different people in each group. They can't affect each other's scores, and the groups are not matched or correlated in any way. And what we're looking for, the t is actually calculating the difference between the means of the group, first group, minus the mean of the group of the second. So the top of the equation is mean of group 1 minus mean of group 2. Now, it is important to note this because this means that it's pretty arbitrary what is group 1 and group 2. So if you're wanting a positive t-test, you want to make sure that basically you have the larger group as group 1 and the smaller group on whatever your outcome is as group 2. And a lot of times people make this adjustment after the analysis is done, especially if they actually have a hypothesis that's directional. But if you see a negative t-test, all that tells you is not necessarily the direction of the relationship, because this is not a correlation. It's simply comparing two groups. It basically tells you that in that case, the second group had the higher score. So the first group minus the second group gave you a negative number. Whatever that numerator is, we then divide with the amount of total variance within and between each group. So basically, we have mean differences divided by total variance. And again, the positive and negative only reflect how the groups were entered or coded. The degrees of freedom for this equation and for when you report this is the total number of people in your first group minus 1 plus the total group in your second group minus 1, or simply the total number of people in your study minus 2. So again, let's think we've done a study with 10 people in group 1 and 10 people in group 2. So 10 minus 1 is 9, plus 10 minus 1 is 9. 9 plus 9, degrees of freedom is 18. Or we just take the fact we had 20 total people, big N minus 2, again, 18. Whenever you see notation of a small n, that usually refers to a subgroup in a statistical analysis. When you see big N, it's usually referring to the total. So for example, if I had a more complex analysis where I had 30 people total in my study, but 3 groups of 10 each, which would not be appropriate for a t-test, in that case, if I was talking about all 30, I'd use large N. If I was talking about the 10 in each group, I'd be using small n, and usually the notation, group 1, group 2, group 3, etc. So that's just what's happening theoretically. In the next set of slides, we'll start going into a little bit more of how we actually analyze this and what we're looking for.